Next up, we have Pierre-Hugues Stefanuto, who's Senior Scientist and Lecturer at Liège University in Belgium. His research interest is in development of analytical solutions based on GCMS, interested in development of statistical models for method optimization and data handling. The driving research goal is the development of multi-omic screening that tackle biomedical challenges at the molecular level. And the talk title is Translating Breath-Based Asthma Phenotyping into Clinical Practice. Welcome, Pierre. Thanks so much for joining us.
Good morning, everyone. I hope you are all doing well in this particular situation. I would like to thank Allstone to give me the opportunity to share my research with you virtually, even if I would have preferred to do the trip to Cambridge. Today, I want to share with you the vision of the University of Liège on how to translate breath-based asthma research into clinical practice. So, to start, a bit of context about asthma. Asthma is a growing concern everywhere in the world. We see a huge increase of cases. More than 300 million of people are affected with asthma, and we have a big proportion of children there that see their life affected forever with asthma. Moreover, it's a huge burden for healthcare costs. So in Europe, in 2018, we spent almost 20 billion to treat asthma. And I say to treat because, unfortunately, we cannot cure asthma. To give efficient treatment to the patient, we need to properly phenotype them. And it's quite an invasive process. It requires sputum, and some adults cannot produce sputum, and if they can, it's not really pleasant, and most of the children cannot produce a sputum, so we cannot phenotype them using the gold standard. The result of this situation is that 20% of the asthma patients are receiving the wrong medication. And this medication often requires corticosteroid, which is not something that you want to give to patients if they don't need it. So a way to approach asthma phenotyping would be to use breath. So breath is a growing field. If you are here today, it's because you have interest and you trust its potential. So we decided to go to breath and see what can breath do for better asthma phenotyping in the future. So as analytical chemists, we first look to the technology used, and you can see that there is a high variability of analytical method. The leading one are GCMS and direct MS technique, but you see that there is a high proportion of sensors which aim to be faster and more sensitive than classical approaches. So we need to find the technology that fits our purpose. So what can breath tell us on asthma? So we had the chance a couple of years ago to get involved in the BreathSprint study. So what is BreathSprint? BreathSprint was a large-scale study between Maastricht University, Liège University, and the University Hospital of Liège, trying to see if we can use breath information to phenotype patients. It was based on more than 500 patients, and it was quite a successful one. So going directly to the conclusion, we can see that using a couple of markers that were validated, we can differentiate the different phenotypes. And an interesting story behind this slide, it's the slide that we used to present the result of BreathSprint to the clinician at the end of the study. And during the discussion, they say, well, this is great what you can do, but it's not really what we are doing in the clinic. And we were like, okay, so what is the relevance of all our work for clinicians? And they say, basically what we need, it's an approach that allows us to identify a phenotype among the asthma population. So we went back to the computer and we tried to ask the data a different question. Can you pick a specific phenotype in an asthma population? And we did it with eosinophilic asthma. And we compare that with classical eosinophilic asthma diagnosis method like FeNO and blood cell count. And you can see that the VOC are performing as well as the other. They have the same figure of merits. But what was really interesting is when we start to think, well, clinicians are using all those techniques together, so why we should not do the same? And we build a new model combining them all. And you can see that the green curve is performing much better than every single system individually. So this was a really encouraging approach for us to say, okay, there is something there for breast and asthma phenotyping. So to move in the second phase of that study, we're like, okay, what about clinical implementation? How can we put this breast technique into the clinic? So the first approach was to use GC-GC IRES. So what did we do? We sampled the breast in a Tedlar bags, we put it on a TD tubes, and we inject it on a multidimensional gas chromatography coupled to high resolution time-of-flight mass spectrometry. So what is behind that? Behind that, it's a big machine, a big and complex machine that allow you to see the entire composition of your sample. Unfortunately, this system is quite complex and requires high level of expertise to be used properly, and it has a high cost. So we decided to compare it with SIFT-MS. So SIFT-MS, it's a direct MS technique that is using different chemical precursors to create different type of ionization before the MS detection. The advantages of the SIFT is it's much faster, so it's 3 to 5 minutes for an analysis. It's expensive, but not as expensive as GC-GC, and it's much easier to use because you can directly that program button and train a technician or a nurse to use it into the clinic. So this is more a tool that you can see in a doctor office than a GC-GC high resolution TOF. So why do we see these differences? So a GC-GC system has 2 gas chromatographic dimensions coupled through a modulator before a high resolution detection. So this high separation capacity allows you to see all the chemicals present in the breast, and the mass spec allows you to identify them with a high level of confidence. On the other hand, SIFT-MS is specific due to its precursor, but when you use it in full scan mode, you don't know exactly which compound you are monitoring. You monitor a pattern. So you lose a bit of information compared to GC-GC. But on the other hand, the chemical reaction and the instrument design allow you to have something that is directly quantitative. So every single ion channel are comparable and linear. So it's much easier to build a statistical model on those type of data. I will discuss that a bit later. So the result of the study has just been published last month in Scientific Report, and the aim of this comparison was really to see the complementarity and not to benchmark instrumentation. Why we should use GC-GC in some situation and why we should use SIFT-MS in other situations. So to achieve that, during the validation study of BreastSprint, we took a subpopulation in this validation study and we analyzed for the same time point one breast sample on the GC-GC system and one on the SIFT, and we compare what was obtained. So sampling and instrumental use was optimized. I will not go through that. And we had a decent population. 50 participants, we had to exclude 10 of them because we didn't have sputum, or we had some sample that didn't work on the GC-GC or on the SIFT. So we had 40 samples with a breast analysis on the GC-GC, a breast analysis on the SIFT, and a sputum as a gold standard for phenotyping. And on the top of that, we had a layer of some technical replicate for both instrumentation. When everything was acquired, we tried to design a data processing workflow that is comparable, not identical because the techniques are different, but that are comparables. And you can see here that the main difference is it's during the pre-processing. The main drawback of GC-GC for now is the alignment in data queuing. So for people that are used to do large-scale chromatographic analysis, you know that you need to align all your data and after to remove all the artifacts to make sure that all the signals detected are really chemicals and not just noise. On the SIFT, in the other hand, you have no need to cure the mass spec because it's a pattern based, so we want to keep everything. In addition, in the SIFT-MS technology, you can directly normalize your ion channel to make sure that they answer on a linear way. That will be linked to a direct quantification if you use target approaches. So this is really nice because you know that you are linear, so you know that your data will not be too much of a pain to process. Based on that workflow, we start first with unsupervised PCA, just to do a data quality check to make sure that we have no outliers, that there is no trend. So both of the data are highly dimensional. So we have hundreds of variables, ion channel for the SIFT, compounds for the GC-GC, and 40 samples. So this is what we were expecting, just like no specific trends, because it's a restricted population. It's not healthy versus disease. It's phenotype versus phenotype. So the variability is much lower than what we can expect. Going through the whole workflow, we build the RF model to try to see using all the variables what we obtain. From there, we use mean decrease accuracy cutoff to select some features, and we build a new supervised random forest. So I see already the question coming. Validation is required because, of course, we were only able to cross-validate the data with the same dataset. So now we need an external dataset to confirm the numbers. So the only thing that I can say is that both data were treated equally. So we can compare the two techniques even if they are not absolute truths for the power. And if we have a look to the figure of merit, we can see that for the unsupervised random forest model and the supervised random forest model after feature selection, basically the figure of merit are similar. So as I say, the overfitting is present in both techniques and they are comparable. So we see that even if they provide a different level of information, they still allow to phenotype asthma patient. So this is really nice because if you want the chemical information for fundamental research or for treatment development, you can use the GC-GC information. And if you want just a screening tool in the clinic, you can go for the SIFT. So similar performances on the proof of concept, we need to go deeper to really affine the numbers. So every method has its strengths and how can we exploit it? So GC-GC, of course, its strengths, it's the identification capacity. So as a first screening, we can do group type analysis. So we have the chemical family and see if we have like overexpression in some of the phenotype. And if we want like more specific marker, we can use the mass spec, like the fragmentogram compared with library. We can use the high resolution to confirm this identification, and we can use the chromatographic information to reach up to level 2 MSI identification reliability. So this is great because it's in one analysis without any standard. So it gives you a decent level of confidence before to start anything else. And this is the result that we obtained. So in this study, we had 10 compounds that passed the cutoff on the mean decrease accuracy. And you can see that for all of them, we have like the MS library match, the probability of identification, and we evaluate the MSI level of identification. And you can see that we can go from 1 with non-anal that was identified with the standard, up to 3 where we are not really sure of the branching of hydrocarbons, which are really the tricky compounds with mass spectrometry and electron ionization. And I want to focus on non-anal because it's really an interesting compound. So it's a compound that was already part of the first study, the large-scale study, BreathSpring. We also identified its in vitro model of asthma that we published recently, and we found it here again. So regardless the population and the type of sample, when there is asthma mechanism involved, we seem to have non-anal as a marker. So it's really a compound of interest for asthma research. So what is the strength of SIFT? So the big power of SIFT-MS is in its precursor. So with the SIFT instrument, you can get up to 10 different precursors that are positive or negative. Each of them will have a specific chemical reaction with different chemical families, so a specific ionization pattern for different compounds. And combining the answer of this precursor, we can have a high level of specificity. In this study, we use 3 precursors, H3O+, NO+, O2+, and in the first processing that I show you, we use them all together. So we had a bit more than 200 ion channels for each precursor, and we combine them to have a big database of more than 600 ion channels. We process them, we did feature selection with random forest, and we build a model. But every single precursor is an independent analysis. They are taking place all together in the mass spec, but we can separate acquisition from one precursor to another. So we can treat them as individual analysis and have a single model for each of them. And it's what we did. And we can see there that we have different accuracy and different behavior on the PCA for the different precursors. So we can now tune the selection and the model building based on the precursors that are most relevant for us. And here we did it with 3, but the final goal will be to do it with up to 10 and do the method development using all the precursors and after focus on the precursor that have a high information level. So this is really interesting for breast, but it's even more interesting for SIFT processing in general. And this is what we obtain. After that, we have all this single model, and the more informative model, we can combine them and build a new global model based on the single model. And it's what we did for asthma, and you can see that the best performances for us was obtained combining H3O+ and NO+, where we reach almost 0.9 area under the curve. And we can see on the PCA that we have a trend to separation too. So we have really a way to tune the processing to see what are the best precursor to react with the asthma marker. So that was really interesting for us to see what we can do for asthma with the SIFT, but also what can we do with processing tool for full scan SIFT-MS data. So in the future, as I say, we can use more precursor to refine the model. We can use different fusion approach, different machine learning tools. So this is just the beginning of our research in the area. So take home message, it's possible to phenotype asthma patient based on exhale air. I think this is something that we can state now. So we have a large scale study that show that, and we have a proof of concept study that show that on different analytical platforms, we obtain an information. So there is something there, even if we don't know exactly what. So it's working with both technique, and as long as the analytical workflow is optimized and you compare instrument at the best, you can have really a complementary information from the different piece of the puzzle. So the final goal will define the best approach. It's what I was trying to pass as a message during my presentation. GCGC provides you chemical information, highly informative for fundamental research. SIFT-MS, it's fast and easy to use. So this type of instrument is, I think, the future to go into clinic. So, of course, this is the work of a full team. So the clinical team, so the pneumologists that are like following the patient, recruiting the patient, the technician at the hospital that are doing all the sputum characterization. This is a huge amount of work, so thanks to them. Thanks to the analytical team that are like running the sample, processing the sample. So a lot of fun, but a lot of challenges are answered by this team. So thanks to them. If you are interested by multidimensional chromatography, we are hosting a workshop in February. It was supposed to be on ground, but of course, like a lot of events, it will be virtual this year. So don't hesitate to Google it or drop me an email and attend the workshop. It's completely free to attend, so don't hesitate to have a look if you're interested by the techniques. And with that, I would like to thank you for your attention, and I will be really happy to answer your question.
Thanks so much for that. So the first question is, were the patients clinically stable? Were they on any treatment? If so, were those treatment phenotypes specific?
Yeah, so the patients were all stable. So because there are different phenotype and different like type of asthma, allergic or not, they have like so much like variation in the potential treatment that the only control that we can say is to ask them to be stable to enter the study. So they were stable. They were on different drugs. So that was also a large part of the demographic data curing, where we had to make sure that we had no correlation between the treatment and the VOC profile. And what we see, it's like mostly the treatment has no effect. It's more the way that the patient is taking the treatment. Like, is it like taking it like on a regular basis? Or when you think about that, that's a major it's a major problem than someone having a treatment or another treatment.
Brilliant, thank you. So next question is, was there overlap between misclassified patients among GC-GCMS and SIFT-MS?
Yeah, there was not really a big overlap on that. So there was not like a patient that was like misclassified, like in both techniques that you can say, oh, maybe it's the gold standard that is making an error. So that we didn't observe. So we had different ones that were like ruled out of the phenotype during the study.
Excellent, thank you. Next question is, I would expect that the number of detected VOCs in GC-MS is higher than with SIFT due to different ionization processes. What were your experiences? If this is the case and SIFT shows less substances, doesn't this mean that the possible, doesn't this mean that the possible biomarkers are excluded? If so, what does this mean for possible outcome of a study?
Yeah, this is a really interesting question. So when we start that study, like most of what was done like between GCMS and SIFT was like identifying biomarkers with GCMS that is powerful but more complicated, and trying to transfer that in a target SIFT-MS approach. And for what we know, it was not really successful, because like even if it's untargeted breath screening, like the way that you will sample, the fact that you use TD or not, like it's changing. So it's not the same thing that you send in the mass spec at the end. And the response of your detector due to the ionization will not be the same. So we decided to like put that on the side and say, we will do a fully untargeted study on both sides independently. So we didn't try to use the chemical marker from GC-GC in the SIFT. We say one is giving us chemicals and we can use that as markers. The other one is more MS patterns, and the variable are ions. So most probably some compounds are highly sensitive to chemical ionization, and they are like more abundant in the SIFT and not so much abundant in the GC, and the other way around. But here was not trying to transfer one compound from one side to the other. It was more to say, there is something in the breath. Can I exploit it with GC-GC to really understand the mechanism? And can I exploit it with the SIFT to try to make a rapid tool that I can put in a clinic?
Okay, thank you. Next question is, how do you provide the breath sample, the SIFT-MS, via Tedlar bag or direct exhalation into the instrument?
We use Tedlar bags. So for both sampling, we use a Tedlar bag that we connect directly to the SIFT, just because it was like, on a logistical point of view, was the only solution for us.
So time for one last question. In the combination test using VOCs, eosinophils, and FeNO together, did you look at combining pairs of techniques? Do VOCs add anything on top of combination of those other biomarkers?
Yeah, so we did like all the pair comparison before the all like technique comparison, and every time you add an extra layer of information, it's improving the classification accuracy. So there is no real correlation between FeNO and breath, and FeNO or breath and blood eosinophilic count. So they are not like providing the same level of information for the classification. So more we had, better we have classification there.
That's interesting. So it's complementary information. So the combination gives you more than the, okay, that makes a lot of sense.
Yeah, because for us, we were really expecting something like correlate with FeNO? Like, do we have one compound that it's produced the same way that FeNO is produced, and we can like really correlate that? But like Roy mentioned it, like for that we would need like maybe like exact quantification on the GC data to have like really like a ppm level of FeNO with a ppm level of chemicals in the breast.
Excellent. Okay. Well, thanks so much. The rest of the questions will be answered just through the type discussion. We've got to move on. Thanks again. No, that was fantastic.